Now let's talk about Mealy finite state machines. Mealy finite state machines differ from Moore type finite state machines in that the outputs are determined by the current state and the inputs for Mealy FSMs. So let's design a Mealy FSM and a Moore FSM to solve this problem. Alyssa P. Hacker has a snail that crawls down a paper tape with ones and zeros on it. The snail smiles whenever the last two digits it's crawled over are 0 and 1. So we're going to design both types. So we've already designed Moore type FSMs, and we'll show the difference between Mealy and a Moore FSM. So this ticker tape is essentially an input that is going to change from 0 to 1. And so here's our Moore FSM. We'll draw our state. So remember, our states are circles. So we have a state here. And whenever there's a 0, we'll go to the next state on the input. And I'll say, hey, I detected a 0. Now all I need is a 1. And then I can, output a smile. And so if there's a 1, then the output should be, the smile output should be true. Just put smile. So smile is shorthand for saying smile equals 1. So that output smile is going to be equal to 1. So we start by looking at the sequence that we want to find. So we want to find this sequence of 0, 1. So what happens when we don't find that? So let's see what happens. So we're in this state. We can call this state 0. This one's state 1. This one's state 2. If we're in state 0, what we call the reset state, that's where we go up upon reset, haven't found any bits that we are interested in yet. And if we get a 1, still haven't found any bits that we're interested in. And notice that we've covered all of the cases. We deterministically know what the next state should be depending on the input. If I don't include that last transition, this arrow here, then we won't know what to do. The FSM doesn't know what to do if it gets a 1 and it's in state 0. And that would be an error. So now we know what to do if we're in state 0. What about if we're in state 1 and we get instead of getting a 1 that we want, we get a 0? Well, it's possible that that's the first 0 of a sequence 0, 1. And so we can stay in that S1 state to say, hey, I found my 0. Still found it. And state 2, we don't have any transitions out of that. So let's see what happens. So we could have a sequence, for example, 0, 1, 0, 1, 0, 1. Well, here's the sequence, here's the sequence, here's the sequence. And so if we just did something like this and said, oh, okay, well, let's go back. We're done. We found it. Then we would miss on that clock edge, could have had a 0, which was the first bit from the next sequence. And so instead of that, that would be wrong. We would go, hey, if I get a 0, I want to go back to the S1 state to say, hey, I found my first 0. Could be the first 0 in a 0, 1 sequence. But if we would get a 1 and we're in that last state, the S2 state, yeah, still haven't found anything interesting. Right, in that case, we got a 0, 1 followed by a 1. Well, that can't be a part of a 0, 1 sequence. So we just go back to the reset state to say, hey, yeah, I haven't found anything that I want to find yet. Okay, so that looks good. More FSM drawn a little bit more nicely here. And now let's draw the Mealy FSM. So we still have our states being circles. So if we find a 0, we want to go to a state that says, hey, I found a 0. But now here's the difference. For Mealy FSM, we draw the output on the transition instead of within the state. So here our output, that's our smile output here. Our smile output is 1. Because there's just one output, we can just put 1. The only output should be a 1 there. It should be 0 in every other case, our output. But now our output is drawn on the transition. And so the output, in this case, right, we just found the 0. So yeah, we don't want to output 1 yet. We've only found a 0. And so now what happens is, well, what if we find a 1? Well, We're in S0, find a 0, and now we go to S1 and we find our 1. Well, now we can do this. We can say, well, I'm in S1, and now I can say, okay, well, I found a 1 here, and that's what I wanted. I wanted to get that, and so now my output should be a 1. So Mealy FSMs, we have the input slash, on the other side, we put the output. And these are our transitions. And so if we're in S1, now we do the exceptional cases. We always do the cases we want to find first. We always include our reset input here. It's a common error to forget that. Now if we're in S1 and we don't get a 1, if we still get a 0, well, that's fine. We still have our first 0 that could potentially be part of a 0, 1 sequence. And we stay in S1. If we're in S1 or S0 and we get a 1 input instead of a 0 input, well, didn't get anything we wanted. So we stay in that state and we haven't found the sequence for sure. So the output should be 0. And so drawn more nicely, here is our Mealy FSM, and you'll notice from looking at it, hey, guess what? We have fewer numbers of state. We have 3 states here and only 2 states in our Mealy FSM. So now let's see how we turn this into a circuit. So now let's look at how we turn this into a circuit. So more FSM. The more FSM state transition table, done this before. We went ahead and encoded the states. S0 is 0, 0, S1, 0, 1, 1, 0, binary encoding, state bit 1, state bit 0. So if we're in the 0 state and A is 0, this transition here, it goes to the S1 state. And again, we're going straight to the encoded state transition table. At first, I'd recommend doing the unencoded table first and then encoding it. If we're in S0 and we get a 1 instead, we're going to go back to state 0. If we get a, if we're in state 1 and we get a 0, we're going to stay in state 1. If we're in state 1 and we get a 1, we're going to go to state 2. If we're in state 2 and we get a 0, we're going to go back to state 1. And if we're in state 2 and we get a 1, we're going to go back to state 0. And now we can write our next state equations. S1 prime is just S1 bar and S0 and A. S0 prime, write this, you put this into a K-map too, or you write this out and it would end up being, you can minimize it using a K-map or Boolean algebra. S0 prime is A bar. K-map is much easier. And so now we have our next state equations for our more FSM. And we can also do the output table. Remember, for a more FSM, the outputs depend on just the current state. They do not depend on the inputs. And so the only place we get a 1 on the smile output, which is labeled Y here, is in state 2, which is encoded as 1, 0. In the other case, we get a 0. And so we have the output Y or smile is S1 and S0 bar, or we could take advantage of don't cares So for example, here's our K-map for this. And we have output of 0 for those two cases. 1, 0 gives us 1. Well, what about 1, 1? The 1, 1 state. Well, we don't have that. We're not using that in this FSM. It's an unused state, so we can put a don't care there. And then we can circle that and say, okay, well, y is just equal to S1. So for a Mealy FSM, we actually combine the state transition and output tables because the next state and the output are both determined by the current state and the input or inputs. So we have two states. We only need one bit of state. We've used binary encoding again. We could have used one hot encoding. So we have a single bit of state bit sub 0. State S0 is encoded as S0 equals 0. State S1 is encoded as S sub 0 equals 1. And so if S sub 0 for in state 0 and A is 0, so here's our A input, it is 0 there, then, well, our next state should be state 1, which is 1, encoded as 1, and Y should be 0. And Y should be 0. If we're in state 0 and we get a 1, this next case here, then the next state should be state 0, and our output should be, again, 0. If we're in state 1, now we'll do the state 1 cases, and we get a 0. Well, next state should be still S1. The output should be 0. If we're in state 1 and we get a 1, there's our 1. If we get a 1, then our output, then our next state should be state 0. The output should be 1. And so now we can write equations just like before. S0 prime equals A bar. So we've written out as sum of products and then we've reduced it. Or put it in the K-map. And then Y equals S0 and A. So now we can draw our schematics. We have our next state and output equations for the Moore FSM. We put our state register, we draw our next state logic, and we draw our output logic, in this case the Y output, or what we called in the problem the smile output is 1, and S1 is 1. And we can draw the Mealy FSM schematic in the same way. In this case, we have one bit of state, so we have a 1-bit state register. And we have our reset input always, reset and clock inputs. And then we also have our input, input A. Input A. So S0 prime. So here's our S0, the state bit. This is the next state bit, is equal to the inverse of A. And Y, or the smile output, is equal to S0 ANDed with A. And so we see that we have some next state logic. Here's our next state logic for our Mealy FSM. And our output logic, unlike the Moore FSM, that was only, the outputs were only determined by the current state, the output is determined by the current state and the inputs for a Mealy FSM. So most of the FSMs that you're going to encounter or design are Moore type FSMs, but Mealy FSMs matter when we want the output to respond immediately to the input change. So it's really, Mealy FSMs are only used when timing is critical, and responding to the input change has to be fast. So if we look at the timing diagram for the Mealy and Moore FSM, we can see that, well, here's our input A changing from 0, 1, etc. And so here we see a pattern. And our Moore FSM on the top here goes from S0. And once it detects that 0, it goes to S1, next clock edge. And then once it sees the 1, it goes to S2 at the next clock edge. And then we see the output changing at S2. So one cycle after the 0, 1 sequence was detected, we see the output changing to, or asserting to 1. However, with the Mealy FSM, well, we see it sees the 0, and the next state becomes S1. So it still does wait for the clock edge. Go to that next state, S1 here. But while we're in S1, we can see that, well, it detects the 1 and immediately asserts that output of 1. So it sees this 1 on the input and immediately asserts. Says, hey, I'm in S1, I'm in state S1, and I saw 1 on the input. Great. Let's go ahead and assert that output. And so it asserts 1 cycle earlier than the Moore FSM.